Okay, today we're going to continue in the SNR in the AM system. Okay, we have been through this last week, but I just go through it as well, that's just like a recap. So this one is a double sideband suppressed carrier. Okay, double sideband suppressed carrier synchronous detector. Okay, so you learn from the previous. Okay, you have super heterodyne receiver. This one is for. This is for what? Okay. Okay, we go first here lah. Okay, the super heterodyne receiver. So you have RF signal. This is the flow lah. Okay, when we have super heterodyne receiver, you are being introduced to IF. Okay, which is intermediate frequency. So it is for the AM, it is 455. Okay, but for the FM, it is different. So we will look at the table later on lah, which you already go through last week. Okay, so what is a heterodyne? Okay, heterodyne is actually a mixing of frequency in a non-linear device to produce new frequency. Okay, to produce new frequency. That is concept of heterodyne lah, means it's a mixing of frequency in a non-linear device. Okay, to produce a new frequency. Okay, it is easier and that's basically working in low frequency lah. Okay, because one of the advantage that we're going to standardize, okay, the into one frequency, and it's easier if we standardize to one frequency and all the components that we choose to work with it will be based on one frequency. That's why we introduce this as well, this concept. Okay, for example, okay, and then for the component, if you have component working in low frequency, it is more easier and is less expensive. If you have component that is working in high frequency, okay, sometimes it is complicated and it is more expensive. So this one can be, let's say if you have question, why we want to do heterodyne in the first place, why we want to do it. Okay, so that is one of the reason. Okay, one or two of the reason. Okay, it is easier and less expensive to work in low frequency. So that's why we bring these components into low frequency, and we introduce the concept of IF. Okay, for example, amplifier. Okay, for example, amplifier, it is more stable and has a high gain intermediate. Okay, if we use at the low frequency. So this is the frequency conversion we have gone through last week. Okay, so this is local oscillator. So we can have carrier minus of or intermediate frequency, or we can have carrier plus intermediate frequency. So you can have either one, this one or this one. Then depending on your selection, you will have different resulting equation. Okay, for here you're going to have, for example, if you say WLO equals to WC minus WIF, if you insert into this equation, end up you're going to have this. Okay, you can just test on your own. Okay, this one is just substitution, and the next one, if you substitute WC plus WIF into this equation and this equation, you end up will be getting this. Okay, I just go through so fast. Then we will go through from this XT, the one that we choose just now. Then we go through the band pass filter, which is tuned to our intermediate frequency. So we're going to filter out everything. Okay, and we only take the one that which is IF. Okay, so it is we take the one that operate at low frequency. Okay. So the resulting will be A plus MT cos omega IF T. Okay, so you see here, right? Instead of having carrier, okay, instead of having the higher frequency, we are now having only intermediate frequency, the 455. So the advantage, disadvantage of why we want to do the super heterodyne. Just now I speak briefly what is heterodyne. Okay, and why we want to do it. Okay, so this is properties for AM and AFM radio. So you have this for AM radio. So RF carrier range is this, and RF frequency is 455 kilohertz. Okay, this one is wrong. 0.55 megahertz. I think I asked you to do correction last time. Okay, then we have IF bandwidth is 10 kilohertz. So if for FM radio is 88 until 108 megahertz. Okay, this one is megahertz, so where you can see how different it is. It is very small compared to this one, okay, in terms of frequency. And the frequency for FM radio is 10.7, and we have the bandwidth, which is 200 kilohertz. So 30 times more than here. Okay. So now, this is the SNR system. We have gone through this week, also last week. Okay. So you see this one. What's the point we put this square root of 2 is actually easy for calculation later on. Okay. Where we end up cancelling. Then because you see. Okay. So if you know for the VRMS, for example, right? For the VRMS, this one I'm surprised because I was being asked during the class last time. I mean during the test, a student asked me this question, how to do the RMS. So actually, you should know, and actually, don't really depend on the appendix. But two students asked me, but end up I just tell. But actually, no need. Okay. But you know this one already you learn from your secretary and other subjects, electrical side. VRMS is usually Vmax over the square root of. So that's why we introduce, okay, you can see that we introduce square root of here, right? It's actually, in the end, it's easy to cancel out. Okay, it's easy to cancel out. If we have another square root, then it will cancel out it here. That's why we have this. Okay, that's why maybe you are wondering why we suddenly have square root of 2. Why we don't just having why we not just having Vm cos t. Okay, so the received modulated signal, you can see square root of 2 Vmt plus Nc cos omega ct and S plus C. So this is actually the noise. Okay, the noise that you receive from the environment. Okay, or from the internal, but it's a noise, additional noise. And then we have NS. This one is coming from the filters. Okay, coming from the filters. Okay, so after we go through low pass filter, of course, when we go through the low pass filter, this one is being cancelled out. Okay, this one is being cancelled out because this one is higher in frequency. Okay. So we will end up with Y not T. Okay, here, which is VMT plus half of NCT. So then after that, we have input signal power. Okay, SI square root of 2 VM cos omega C 2T. Okay, so this one is actually RMS. RMS. Okay, I think this is RMS. You can refer to the module if you want to have more readable equation. Okay, you can refer to the module. Okay, so don't forget there is square here. Okay, and then VMT square. Okay, so input signal power. Okay, input signal power, the one that we receive. Then we have input noise power. When we have input signal power, we will also have input noise power, which is Ni. Okay. So the question in the exam, in the test, I think it's asking about noise power, right? So it's just Ni equals to, I think equals to KTB lah. Okay. The test one question. So try to solve the question. Okay. What if you receive? What if the question asks you for output noise power, the one that I asked you in Telegram? Okay. If you done this, maybe we can discuss in the next class. Okay. It's interesting. Actually, this is if this is question to be asked in the test one, maybe many students maybe many students will find it's difficult lah. That's why I think this one is more easier lah. Okay, so try this. because this one still can be solved because all the question in the test one already have the information required for you to calculate what is the output noise power. Okay, so this is double sideband suppressed carrier for output signal power. So the same in terms of Vm square T. Okay, so then we have output noise power. This is output signal power. This is output noise power. Okay, so the ratio is SO over NO. So this one is SNR. Okay, signal to noise ratio at output. Okay, at output. So this one not to be mistaken. This one is B, not beta, because FM you will have B. FM you will have beta. Okay, beta is a modulation index in FM. Okay, modulation index for FM. For AM, you go, it is in M. Okay, modulation index for AM. Okay, now is I think this one not yet. Okay, now is single sideband suppressed carrier. Okay, single sideband suppressed carrier. So you can see the difference. For the single sideband suppressed carrier, you don't have square root. You only have VMT. And instead of square root, you have 2. Okay. So again, this one is to, I think this one is one of the reason, very obvious. This one is for to make the calculation easier. Okay. Why we don't use VM cos omega CT, right? Okay. So the same reasoning, I think. Okay. So you have this one is the additional noise. Okay. That you have. Then together it is you're going to have input signal. Okay, and you have input noise. Okay, input signal power and input noise power, and they are together YIP. Okay, so VMT cos omega CT VH sin omega CT plus NC omega NCT 2 cos omega CT. So here, okay, sorry, yeah, there is a modulation signal 2 cos omega CT. No, this is here. Sorry, this is here. Okay, not yet go through the mixer. So we have VMT, NCT, cos omega CT, and S sin omega CT. So this one you can see, this one is the noise. This one is the noise. Okay, the similar as what you have in the double sideband suppressed carrier in the previous slides. Okay, so mathematically this one you try to understand and you try to do the exercise. I think I have been given the past final exam. You can try that. Okay. Whenever we already touched about this, we already covered this. You try to do the exercise. Perhaps in the next class, in the next physical class, we try, if we have time, we try to cover the exercise. The one that I owe you, which is the exercise. I think exercise 3. Module amplitude modulation, exercise number 3 for chapter 2. Okay? I ask you to do first and we discuss later, right? So we discuss in the next physical class. Okay, this one, exercise 3 module. So input signal power SI, this one is 2 VM cos omega CT square. Okay, and then square root. In the end, you see, it will be cancelled out. Right? So that's why the point where we will have that. So in the end, you have this. Okay. So next, this one is mathematics. Output signal power Y not T VMT plus NCT is the noise. Okay. This is your modulated signal. Okay. Sorry. This one is your message signal. Okay. At the output, means we already filter out everything and we already retrieve back the original signal with the noise. Okay, then we have output signal power. Okay, output signal power, which is S0, okay, equals to VMT. So this one is I think you know this one is VM over square root of 2. Okay. So refer to the module. Okay. This one is not a typo. There is a meaning why we use this bar. Okay. Then we have output noise power. So similarly like this one. So we have NCT square. Okay. And then you have eta. This one I forget what is the how you pronounce this. Okay. Then we have B. Okay. So this is a noise spectral density. We call this as a noise spectral density for single sideband. Okay, for single sideband. So remember this name. Okay, thus ratio output signal to noise signal power. So the same. This one is SNR. SNR output. SO over NO. So VMT square, which is the one that you have here. Okay, now you put it here. And then this one is the output noise power. Then you have this one. Okay, DSB-SC and SSB-SC have the same SNR. Okay, double sideband suppressed carrier and single sideband suppressed carrier have the same SNR output for a given transmitted power in transmission bandwidth. So you can see that here SNR, okay, SNR for double sideband suppressed carrier is the same as the SNR or single sideband suppressed carrier, given that, okay, given for a given transmitted power and transmission bandwidth. It must be the same, right? If it's different in terms of transmitted power, difference of bandwidth, of course it will be different, right? So for a similar given value of transmitted power and transmission bandwidth. This one is a full AM. Okay, full AM means double sideband, full carrier. Okay, double sideband full carrier, synchronous detector. Okay, so again you see we use here square root of 2. So if you notice for double sideband, okay, for the double sideband, regardless it is full carrier or suppressed carrier, but at least it is double sideband, you can see it use square root of 2. Okay, let's we go to the previous slide. Okay, you can see is the relation. See, this one double sideband, it used square root of 2. Okay, although it is although it's suppressed carrier, as long as it is double sideband, it use square root of 2 here. Okay, but if it's single sideband only, we use 2. Okay, so this is just mathematics to make the calculation easier for later on for cancel out. Now this is double sideband full carrier but still double sideband. Okay, so we use square root of 2. Okay, so this is the general equation of double sideband full carrier and cos omega ct. Then this the noise that exists in the system. Okay, then we together they are mixed up in additional. Okay, the noise is additive in nature, and then you produce you come up with YI, which is the receiver modulated signal, the receive modulated signal with the noise. Okay, then we have input noise input signal power. Then we have also input noise power. Okay, then you can see the local or the carrier that we generate is similar. Okay, cos omega ct means we need to have the same omega carrier lah. Means we need to know what is the carrier being used. Okay, you see here is square root of 2. Okay, you see in here is cos omega ct. Okay, so you need to see the difference. Wait for a while. This one should be 2. This one I think should be 2. Wait. There is like typo in the, like, check the module. I hope, because sometimes if the because we take the slide is from the module or the module is from the slide. So if there is one error detected in the slide or one error in the book, maybe the error can be seen in the book as well. For example, if this, right, if you have seen this error in the slide, maybe the book will have the same error. So that's why I want to see the book. Or maybe this one, this error is coming from the error in the book. This is please. SSPC. SSBSC detector. Cos omega CT. Okay. You see here, okay, this one, if you see in the module, okay, see, you put the, uh, turn to page 62 of your module, okay, of your module, you look at below equation 2.49. After equation 2.49, it mentioned after the multiplier xt equals to rt cos omega ct, then you have vmt cos omega ct plus minus vm sin omega ct plus ni cos omega ct. So here they put cos omega ct. Okay, they don't put 2. Okay, they don't put 2. Okay, because if you see, it is, if you go to page 61, okay, if you go to page 61, 2.112, okay, the below one, 2.112, it is a noise in single sideband suppressed carrier. So this is correct because this one is single sideband suppressed carrier and it's a synchronous detector lah. So this one correct, cos omega ct. So I don't know where is this to come from. Okay, this one. Okay, so it should be cos omega ct only. If I am wrong, let me know. But this one is I am for the book. Because it's weird because this one should be the same way. This one. Okay. Okay. Okay, now this one is the full AM synchronous detector. So full AM synchronous detector, this one is actually in okay, you can see later on the corresponding pages in the module. Okay, so the receive modulated signal, you can here is square root of 2 VMT plus NCT. Okay, NCT here, additive of the noise. Okay, we have the noise and together with the cos omega CT. So we receive, I mean the modulated signal is with the noise, addition of the noise. Okay, and this one is the noise due to the filter. Okay, synchronous full AM very similar to double sideband suppressed carrier with exception to additional carrier. Of course, because this one is full AM, so we have carrier components. Okay, otherwise we didn't have. Okay, so output signal power is SOVMT. Again, this one is not VMT. This one is you having the square root because this is RMS value. Okay. We have output noise power. Output noise power NO NCT square NCT square. So this one is similar to the double sideband suppressed carrier. Okay. So this one is similar as well. Okay, similar. Receive signal is 2 EC VMT cos omega CT. This is the signal that you receive. Okay, the signal that you receive without the noise. Okay, the one that you transmit actually, and the one that you receive without the noise. But then if you have the noise, it is you add with the noise. Okay, so SI is a square root of 2. Okay, and square root of 2, then you have to square it in order to calculate the noise power. Then you have in order to have the signal power, then EC plus VMT is 2 square root of 2 square and over 2. Okay, so that's why we have this square root is being used in the first place, so that you see you can easily cancel out. Then you will end up with this value. Okay, EC square plus 2 EC VMT. So VMT, this also like a RMS value plus plus VMT almost equals to, okay, approximation to EC square plus VMT. Okay, we assume that VMT to have a zero mean. Okay, if you see this one, EC square plus 2 EC VMT plus VMT square. Okay, so you can use this equation, or you can make an approximation. You see EC square here. Okay, then you have VMT square here. I think this one is more easier to write now. Okay, so you must take note which equation actually being put inside the appendix, which one is doesn't. Okay, so in the test is you don't expect all is being given in the test, but in final we will give all. That's why in the test you don't assume that you're going to have the same complete formula. So the same will happen to your test 2 later on. Okay, don't assume that we will give you the entire appendix. Okay, so this is a SNR out. Okay, SNR out means SNR outputs. Okay, is equals to SI over SO over NO, then SI over NOB, and you get this. Okay, I think this one it will be easier if we do exercise. Okay, I have to admit, I think you as well is a bit boring because it's just mathematics without doing practice, then it's a bit difficult. Okay, so since EC square VMT square is greater than 1, okay, because if you know EC is always bigger. Okay, it's always bigger than VMT. Not always, normally it's always bigger, because EC is the one that we generate, and modulating signal is the one that the natural signal normally is less Okay, so since EC is often but not much bigger than VMT, so we will end up it is greater than 1. Okay, the ratio so SNR for full AM, okay, for full AM is at least 3 dB worse than the double sideband suppressed carrier and single sideband suppressed carrier. So what is 3 dB? How you know this? What is 3 dB? 3 dB, for example, I 3 dB, you convert to linear. You convert to the non-log form. What you're going to have? You're going to know that this what does it mean by 3 dB? Okay, so 10 log 3. Okay, you try 10 log x, what you get. Okay, so this is for you to try to explore. Okay, actually no need to explore, I already give you the formula. In the end you will have some number. Okay, so just anti-log actually 10 to the power of 0.3. Okay, so full AM envelope detector. Okay, this is an envelope detector. Envelope detector in the previous lecture. Okay, in the past lecture we have been cover envelope detector, which is the diode detector. Okay, the name. But this one is with the existence of noise. Last time we don't cover noise. Now we cover this one in this lecture slide of envelope detector, if with the assumption of noise is being considered. Okay. So you can see, right, how little test one, how test one don't cover much. Don't cover much. So please study well, because many of the things in the AM is not being asked. Okay. So A plus VMT cos omega CT, and NT is the noise. Then together, we add them together, we have the modulated signal in the receiver part. Okay. Then we have the input signal power, then input noise power. Then this one is the envelope detector, the one that you learned before, the same circuit. Okay. Then after going through the envelope detector, you're going to have the signal again, right? The original signal again, but this time with noise. Okay, with the noise. Okay. So the received modulated signal, YT EC plus VMT plus NCT cos omega CT, okay, which is the carrier, and plus NS sine omega ST. Okay, this one is from the filters. Okay, hence input signal power SI EC plus VMT square square over 2. Okay, over 2 EC square plus VMT. Okay, this one means it's not VM, it's a Vmax. Okay, Vmax over square root of 2, and then over 2. Okay, assuming that EC plus VMT is greater than noise. Okay, usually noise is not big. Okay, usually small noise is, I think, is logic. Noise is not so big, it's just a disturbance, okay, unwanted energy. But sometimes if the system is very terrible, we will have a lot of noise. Okay, but if we assume that our carrier, okay, carrier amplitude and our modulating signal is much greater than our noise for almost all of the value of time. Okay, mean in this case we are considering the noise is small, so small analysis of noise. Okay, small noise analysis means it's different if the noise is bigger. Okay, hence input envelope. Okay, input envelope, we're assuming that EI, okay, input envelope, we're assuming is EC plus VMT plus NCT. Okay, this is it. Okay, for the input envelope, assuming that the noise is very much small compared to EC plus VM. Okay, if you see, this one is your envelope, right? Envelope equation. Okay, then this one is your input envelope, but with noise. Okay, different. Last time your envelope is only this one. Okay, right, without the noise. Okay, the same output signal power. Okay, SO VMT square. Okay, the same as well. You cannot use it doesn't mean VMT square like this. Means you have square root over square root of 2. And output noise power NO NCT square. And this one the same that you have in the previous slides. Hence S and R output for small noise. Okay, for small noise case, envelope detector has comparable performance to synchronous full AM detector. Okay, so the performance is comparable with the full AM without noise. Okay, for the case of small noise present. Okay, for small noise present, the envelope detector with noise, with noise has similar performance or comparable to the synchronous full AM detector. Okay, the one that without noise. If we have large noise, large noise is when we have the envelope, which is much small than the NTA. Okay, this one is not good because your noise is much bigger. Okay, means not good system. Means not system is not good, means that the environment, because we have a lot of noise. Okay, so SO over NO, of 0.916 EC square VMT SI and eta Z naught and B. So this one you can look in the module. Okay, you can look in the module for more detailed explanation. Okay, and the book is using not the book is using much better kinds of writing. Okay, for example, in the book, okay, let me see from the book. Okay, the book here, okay, the output signal power. Okay, for output signal power. So you can see the book, they are not using, they didn't use this. Okay, so I hope that you can refer to the module, because in the module they will give you the much better way of presenting the number lah, the equation, so that it is more obvious. For example, in the module page 64, equation number 2.58, okay, 2.58, equation page 64, they are representing the equation, output signal power, and the output is SO equals to half VM T squared. Okay. So this one is more obvious than this, right? Okay. That's why I ask you to look at the module. Don't really dependent on the slides. Okay. And you can do the exercise number two. You can do the example, example 2.9, example 2.8, and so on. Okay, to get you to familiarize. As I told you, there is no tutorial for this course, because it's already third year subject. You are expected to be more independent in your study, but we'll go through the past test and past final year. I only have that. I don't have tutorial. You can ask other lecturer, they also don't have tutorial. Okay, because this is a third year subject. Okay, so here is a message signal. Okay, let's say you have a message signal VMT 5 cos 1000 pi t. Okay, is transmitted using double sideband suppressed carrier. Okay, double sideband suppressed carrier. Noise with power spectral density of 10 to the power of 5 watts. Hertz to band is added to the signal during the transmission. Get the SNR in unit decibel. So this one, you want to try first, or wait? Can I ensure this card? Better you try later on. Better you try first. Okay. A message signal VNT 5 cos 1000 pi is transmitted using DSPSC. Noise with power spectral. You see, power spectral density is what? Power spectral density is the one that you see just now, right? They look like N. Okay. And 2 bands is added to the signal during transmission. Get the output SNR in the unit decibel. So SNR. So they want you to solve for SNR out. So okay. Okay. You can try. Can you take this answer? Try first. Try first. So the answer is 28 dB. Okay. So try first, because if I give you the work, if I show you this, you're not going to learn, right? So when you try, when you didn't know the how to, I mean, when you don't have the schematic answer, you will try and you will have this 28. You will try lah to obtain until you get 28, something like that. But if you already know, you see the working step, then you will not try. Okay. So the answer is here is 28, 28 dB. Okay, try first. So here, save. I pause record, stop recording. So we will start the next one at 9:25, 9:25 for the FM. Okay. Okay, so relax first. We will continue 9:25. Okay, while we are doing that, maybe I want to see the test, the test question. Hadisa. Hadisa, Hadisa dengar tak?
Dengar, doktor.
Recording is progress. Bukan sudah tutup. Kejap, stop.